Hi, this is Mr. Yeager with physics again, looking into electricity. So we just finished electrostatics, where the charge is being held. Now we're actually looking at what happens if I allow that charge to start flowing. What if I have a conductor, let it start moving around? What can I create from that? So we're going to start off. Okay. Looking back at some definitions again, electricity is again that energy or the charge that is carried by these electrons. If there is energy in it, so that's part of it. Obviously, very good definition, it's the flow of electrons. Okay, but again, energy does involve that. Static electricity is that accumulation of charge. All right, we didn't talk about this one specifically, electric field. All right, but electric field is what creates that force that creates that electric force when another charged object comes into place. That actually is not that important of a definition, but I have it in here. So here we go. Again, static discharge. This would be the idea of when you actually get that electric shock. It's what creates lightning. So it's the movement of that excess electrons from one one charged object to another charged object. Lightning would be cloud to ground. That would be the change in charge going from one object, clouds, to the other object, the ground. Now again, we're not looking for huge static discharge within electrical wires. We already talked about conductors and insulators. Conductors allow electrons to flow. They're basically metals. Insulators do not. They're basically anything not metals. All right. So what we're looking at more than anything today is how are we going to measure this electricity? We're going to start having it flow through wires. How do we measure the electricity? So we're going to look at the three major terms of voltage, current, and resistance. But then we're going to get into a little bit with power and cost. We'll come back and do circuits in a separate video. All right. So we already talked about charge before. All right, where charge is Q. Again, this is capital Q instead of the lowercase q that you use a lot of times with the charge formula. All right, or sorry, the force formula. It is measured in coulombs. All right, there is the way we measure the coulomb. Again, charge is related to how many electrons are present, and so we do have a conversion between coulombs and electrons. 1 coulomb is a lot of electrons, 6.242 times 10 to the 18th electrons. So quite a few electrons involved there. So if you do ever get this question of how many electrons are involved, if you know how many coulombs there are, you can multiply it by this very large number. It sort of takes you back again to chemistry with like the idea of Avogadro's number, figuring out the number of atoms or molecules involved. All right, so one of the first big three terms for all circuits is V. All right, is potential difference. That is the official term for voltage. Obviously, layman's terms, we call it voltage. But what is potential difference? Potential difference is what creates the push between the two objects. All right, a push between the two. Sorry, I'm trying to get my pen back real fast here. All right, that's what we are looking at. There's a push that's created, all right, as it moves from negative to positive. All right, it is related to energy. Basically, we call it potential difference because it has the potential for the electrons to move from one spot to another. What we mainly think of this as, sorry, I'm going to fix this a little bit. What we mainly look at this as, when we look at a battery or anything like that, it's the electrons being forced to go from the negative to the positive end. Because again, they should be repelled by the negative end, attracted to the positive end. So there's an energy factor involved here where they want to go. They have this potential to move, so let's create the wire, and then all of a sudden they do fly. All right? So that is voltage. It is measured in volts. That one's kind of the easiest one to remember. The second one is current. Current has the symbol I. So this one is already one that causes some confusion. The nice thing is the third one is pretty obvious. So V is voltage or potential difference. I is current. Current is actually talking about the official flow of those electrons. How many electrons are actually passing over time? That's what we're basically saying. How many electrons are actually passing? So that's what we're saying there. It is going to be measured in what's called the ampere which you probably can just call the amp, and that's letter A. The last one is resistance. All right, the last one is resistance, is R. So we shouldn't have a confusion too much with the idea of current being I. It's the other one that's left out. All right, so resistance is exactly as the name implies. It is something that's inherent to the substance itself, the thing that's trying to carry the electricity, and it will cause some sort of slowdown or opposition to the flow of electrons. So it's trying to oppose the current, all right, not the voltage. It's going to try to oppose the current. It's going to be measured in what's called the ohm, which the symbol for the ohm is the capital omega letter. Okay, capital omega. All right, and I don't know why my pen keeps on leaving. Let me go back and grab it again. Doesn't like me to this one. All right. So it's measured in ohms. All right. And in relation to that, we're about to get to the calculating part. You will have questions of how can you adjust the resistance, because resistance, again, basically is inherent to the substance, to the object that is carrying those electrons. All right? And so there's different things we can do to change the resistance of objects. The first one is, what type of object is it? Obviously, if you have an insulator, it's going to have a high resistance. It does not move electrons very well. That's what an insulator means. All right? A conductor will have low resistance. All right? It allows those electrons to go. Resistance will be greater with thinner wires. All right? The reason for this is there's less space to flow. All right? What I always make an analogy with electrons and electricity is think about traffic. Cars being the electrons, and then the roads being what's carrying those electrons and making them flow. Whenever you go from 3 lanes down to 2 lanes, things always slow down. 2 lanes down to 1 lane, always slow down. Because if you have all these cars trying to go, all right, and we got to imagine these electrons are going almost the speed of light, all right, they're going to be going very quickly, and therefore you're going to get a lot of collisions. And when they collide, some of the electrons will bounce back and they'll cause other collisions. So the thinner the space, and again, they're going to smack against the sides and everything, there's going to be more resistance. They're going to have a harder time flowing. Longer wires. Now this one might be going, wait, what do you mean by longer wires? Okay? Longer wires, what you're doing is now you're making those electrons travel farther. What that means is there's a greater possibility that they could collide with each other. The longer the wires, the greater the friction that builds up. Again, electrons are matter. They will rub against the sides and create that friction, and that will cause them to slow down. They'll create some resistance. Lastly, higher temperatures. Once again, we're going, well, think back again to chemistry and molecules. Higher temperatures means the objects move around faster. But these electrons are not driving straight. They're driving like they're a wave. They're going back and forth, or like a snake, okay? Slithering back and forth. They are out of control. And so if you go at higher temperatures, that means these things are vibrating and going even faster like this. They're going to collide with more and more and more objects. So all of these things will create more resistance. So what will decrease resistance? What's the opposite of insulators? Conductors. What's the opposite of thinner wires? Thicker wires. All right, and what I can give you an example of is think about the wires on telephone poles. They're much, much thicker. There's these huge, thick cable wires underneath or in the ocean, right along the bottom of the ocean to help transmit signals from one continent to another. All right, that'll decrease the resistance. Shorter wires. Now that one you can't really get away with too much, but again, I mean, this is why, little tiny objects, they're going to just have a short wire to make it like a little toy. They're going to have short wires to make sure they work well. They don't heat up too quickly. Obviously, cooler temperatures. I always use computers as examples, or your phones. Usually when they heat up, they don't work as well. They slow down, and that's because they're not allowing the information through the electricity is not transmitting as quickly. All right? We're very impatient. So this leads us to Ohm's law. Okay, Ohm's law. So this is one of the two formulas. Usually students do very well with this. This is obviously not that complicated of a formula. All right. But Ohm's law is V equals I times R. Voltage will equal current times resistance. Okay? Voltage equals current times resistance. All right? What we will basically see here, all right, and ignore these little things down the bottom. I need to get rid of this. All right? What we will basically see is voltage will generally be what stays constant. If I have a battery, it has a constant voltage. The thing is, if I increase the resistance in the wires, that'll decrease the current inside. There'll still be the same amount of push, but it's obviously going to it's more difficult for it to pass around and flow through a higher resistance. So resistance, we say, will directly relate or inversely relate current. All right, and obviously voltage might be a byproduct of that afterwards. We're not too worried about that. Okay, so that is your formula. Voltage equals current times resistance. You're going to get plenty of very straightforward problems where it's just going to be, actually I think it's on the next page, it could be something like the current is 6 amps and the resistance is 2 ohms. What's the voltage? 6 times 2 is 12 volts. You actually will get those types of problems when we start doing circuits. So it's just V equals IR. This is an extremely important formula. Don't overthink it. V equals IR. Just make sure you get the right unit with each thing. All right. Another formula, going back to charge, the formula for charge is Q equals I times T. Charge is equal to the current times the time that the current flows. Basically saying how many electrons are passing by. That's what that formula is going back to. So it's possible, the longest problem I can give you is I can probably tell you what the Q and the T are, the charge and the time, and maybe the voltage. You have to find I and then plug it into the other formula to find resistance. Okay, it might be a two-step problem. But again, that's the other formula we got there. All right, we're going to skip circuits for now. That's going to be a different video. Go, go, go. All right. Let's get to another electricity formula, electric power. Electric power, as you can see, will be current times velocity, yikes. Current times voltage. It's the rate at which energy is being converted. Power is the rate at which energy is being converted. We already know that. We've done it, and I'm sorry that my pen keeps on going away here. All right. We did the formula for power before as, yeah, we did that. Power equals work over time. Okay? Power is the amount of energy being used. Power is equal to energy over time, the change in energy over time. With electric power, we can do this by simply multiplying the current and the voltage. All right, so again, try not to be too confused. That's what's going to happen is it turns out the current, voltage, and resistance can be manipulated many different ways to obviously solve for either one of those other three factors or for power itself. All right, the formula for, or the unit for power is the watt. I mean, again, you're going to get some good practice with this. These are going to be fairly straightforward. It's going to be, here's the current, here's the voltage, what's the power? And that's it, okay? 3 variable, 2 of the variables given to you, solve for the last one, all right? It's going to be that simple. I do promise you that, all right? There are other ways to calculate power, all right? Again, the initial formula being P equals IV. I can replace V with IR. V equals I times R. I'm going to quit with my pen soon. I'm about to be done with this. Okay. P equals IR. I don't use these formulas too much, but there are people out there that could be like, oh, you know, I give you the current and I give you the resistance. What's the power? All right. Personally, I would go power equals I times V. So I would solve for V. V equals IR. Find that, then plug it in and multiply by I again. But that's what this is saying here. This is I times IV. Or sorry, not IV, IR. IR. Okay. So that's why it's power equals I squared R. Same thing goes with the one on the bottom. Okay, power equals V squared over R. That would just be where I place I with V over R. Okay, so that's what we're looking at with those two formulas. These you don't need to use at all if you don't want to, but if you're like, oh, I want to be super fast and do it in one step, there you go. Okay, obviously you could solve for the you could solve for the missing variable in IV first, and then plug it in from there. That's your choice. Electrical energy, kind of going backwards here a little bit. Electrical energy, again, power equals energy over time. That's what we just talked about. So that means energy, I can multiply time out. Energy will equal power times time. So that's our main formula there, power times time. All the ones below are, again, where I've derived P into its other forms from the prior page. So energy is power times time, solved for in joules. The last thing we're going to do, and I know I'm zooming through it. We got just some different formulas, but again, they're all things we've done before. Energy is just basically how much work can possibly be done. The last part here is they can ask you to find the cost of your power bill. What is the cost of the electrical energy? So again, what we're looking at here is when we call them power companies, okay, Sawney Electric, Georgia Power, these are different electrical companies. All right, they actually are providing energy, not power. So they're going to calculate how much energy you are using every single day. All right, and so therefore we pay for this electrical energy. All right, this electrical energy. And so what they do is they calculate the rate of your energy consumption, and this is known as basically we call it joules over seconds times seconds, which, wait a minute, that's just joules, okay? The thing is, this is too small. This is too small. They think that's too small of a unit. A joule second is a watt, okay? And so instead, they use what's called the kilowatt hour, the kilowatt hour. But again, let me just make sure this is clear. I don't think that came across very well. Let me make sure this is clear. They are charging you for energy. This wacky looking unit here is energy. Joule seconds times seconds. All right? Because seconds should just cancel out, and you're paying for joules. All right? The problem is, all right, a joule second is very, 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 very tiny. They'd be charging you fractions of pennies trying to calculate this one out. So instead, they still charge you fractions of pennies basically, but they do it up to kilowatt hours. All right, and this right here is a watt. Joules over seconds, energy over time is power. But if I multiply that by time, that comes back to energy. It's a weird idea where you're kind of going, what the heck? It's power, it's energy, it's power, it's energy. This right here, this kilowatt hour, is a unit of energy. So they are calculating out energy. So there might be some conversions you have to do to calculate this out. So what happens here, and we'll do the problem, we'll figure out why it's these numbers. The cost of your electricity will be the amount of electrical energy that you use in kilowatt hours times the rate that they charge. All right, times the rate that they charge. So if I run through this problem, which basically is going to finish up our lecture for today, let's see how we get all of these numbers. All right, let's practice some of these things. So you have a space heater that draws 15 amps of current from a 120 volt source. I'm going to write that there. So that's voltage. It is operated on average for 5 hours each day. 5 hours each day. I'm going to just write that as 5 hours per day. Okay? So the first question is, how much power does the heater use? So you will have all the formulas. You don't need to memorize any of these. Power equals I times V. Do I have both of those? I do. So I'm going to just do 15 times 120. 15 times 120 is 1800. Just to confirm, is 1800 watts. So this object uses 1800 watts, okay, when it's turned on. How much energy in kilowatt hours does it consume in 30 days? All right, so let's think about this. How much kilowatt hours does it consume in 30 days? All right, so what we have to do here, okay, is we have to basically create this kilowatt hour unit. But I want to figure out over 30 days. So first off, I need to change the 1800 watts to kilowatts. So this would be 1.8 kilowatts. Okay, 1.8 kilowatts. All right. 1.8 kilowatts, I can figure out how many are used in one day. I'm using this for 5 hours a day. So if I multiply these two numbers together, 1.8 times 5, I'm doing 9 kilowatt hours per day. But how many days am I looking at? 30, so I multiply this by 30, and I get, 270 kilowatt hours. So that's the total amount of energy you are using over 30 days. And so then usually what they do is they give you a rate. It's 12 cents per kilowatt hour. How much does it cost? Basically, you just multiply those two together. 270 times 0.12. This is going to cost you $32.40. Okay? I just multiply. Here's my energy. Here's my rate. Multiply the two of them together. All right? That's what we are looking at in these questions. And that is it. So, again, you're going to be working on some problems with these and hopefully be able to use the formulas correctly as you go through and solve from there. All right, thank you.